Hey everyone! One of the key skills for this first exam and for the amino acid quiz is to understand how to draw a peptide and then how to figure out what the correct charge state of that peptide is at a particular pH. We're also interested in understanding how to calculate the pI of a peptide. So I'd like to take a minute and walk you through the process for doing this. So we'll start with a theoretical peptide called kite. So if we break up kite, and remember the formalism is to start at the N and go to the C terminus. So we start with the N terminus, then K or lysine, followed by isoleucine, threonine, ending with glutamate, and then that with the C terminus. Now, if I'm ever telling you to draw a protein or a peptide, you can always default to 7.4 of physiological pH, unless I tell you otherwise. So I would start by drawing out this peptide at 7.4, just because that's my default. And so we can see here we've drawn all the side chains in. The N-terminal amine is protonated because the pKa of 9.5 is greater than the pH, so will be protonated, or the pH is less than the pKa. Is less than that pKa. If the R group of lysine is protonated, because again the pH is less than the pKa of 10.5, if we pop on over to threonine, you may be really tempted to try and deprotonate threonine, but threonine does not have a pKa that would make it deprotonated the physiological pH. So threonine, don't think of it as an acid. But we do, however, see glutamate being deprotonated because the pH is greater than the R group's side chain pKa of 4.2. And then finally, if we look at our C terminus, we would draw our C terminus as deprotonated because at 7.4, the pH is greater than the pKa of 2. All right, so now let's go ahead and practice this skill that we tried at the end of class. You have to do in your homework. And there's a good chance you'll have to do on the amino acid quiz, and that's to calculate the charge of that peptide at a pH of 1, 3, and 5. All right, so the way that I like to do this, I like to make a table where I chart out the pHs we want to look at in the row, and then the charge of the individual pKa group or an ionizable group at that pH in columns. So a column for each each ionizable residue, and then the total charge. So let's start. And one thing we can do too to remember is we can write the pKa's above the ionizable group names so we don't forget. So the N-terminal amine has a pKa of 9.5, or we're assuming that. 2 for the C-terminal carboxyl, 4.2 for glutamate, and then 10.5 for lysine. Okay, so with that in mind, I'm going to switch over to hot pink because hot pink is my most favorite color. Yes. Okay, there we go. No, not salmon pink. Okay, great. Okay, so at pH of 1, would the amine be protonated or deprotonated? In this case, the pH is going to be less than the pKa, so it'll carry a charge of +1 because it's protonated. Now, let's take a look at the carboxylate. At pH of 1, the pH is less than the pKa, so the amino acid will be protonated. But if you remember, the protonated version of a carboxylic acid, COOH, is neutral, so it will carry a charge of 0. Looking at the glutamate at pH 4.2, again, it's the same thing, where the pH of 1 is less than the pKa of 4.2, but so it will be protonated, but again, the ionizable group on the glutamate is a carboxylic acid group, so we would be neutral when we're protonated, so we have a charge of 0. Then finally, if we look at lysine has pKa of 10.5, the pH is less than 10.5, so we would see it would be protonated, but lysine, when it's protonated, again carries a positive charge, so we'd see a +1. And that's because lysine and the N-terminus are positively charged when they're below their pKa, when they're protonated. So if we add these together, we have a charge of +2. Okay, so next we'll transition over to pH of 3. Now for a pH of 3, I'm going to go through this a little bit quickly. We can know right off of that the pH of 3 is going to be the same, it's going to be less than 3 of our groups. So the N-terminal mean will be the same because 3 is less than 9.5. Lysine also will be the same because 3 is less than 10.5. Similarly, for glutamate, 3 is less than the pKa of 4.2, so we'll still see a nice big fat pKa of 0. However, things are going to turn over for the carboxyl group because a pH of 3 is greater than the pKa of 2 for our C-terminus, so we will have a -1. So if we add these together, we get a total charge of +1. Then finally, if we're at 5, the pH is going to be less than the pKa of both of our amines for the N-terminus and for lysine. So those will still carry charges of +1. Again, 5 is above the pKa of our N-terminal carboxylic acid, or C-terminal carboxylic acid, so if you see a charge of -1, but the pH of 5 is also greater than the pKa of COOH on the glutamate group, which is 4.2, so we'd see a -1 here. So at pH 5, our molecule will have a neutral charge because all those individual charges will cancel each other out. So we've gone through the rationale for how I would do this. By the way, especially for this first part of the semester where we're working with drawing out proteins, or peptides, I highly recommend using pencil because it's easier to erase if you. Okay. So now that we've gone through, we've learned how to calculate the charge of a peptide at a particular pH. We're going to build on that, but we're going to use that skill to help us calculate the PI of the peptide kite. Now, when you're calculating the PI, instead of just taking random pHs, we're going to target specific pHs. And these are the pHs where the pH is equal to the pKa group. So if we were to look at what the titration curve for kite would look like, we would see that there would be 4 plateau regions representing the pKa of the C-terminus, the glutamate carboxylic acid group, the N-terminus, and then the lysine side chain amine group. So 4 different pKa's, so 4 flat areas, and then there'll be 4 more vertical areas between those. And so one of those areas between the 2 pKa's, the total charge will equal 0. We just don't know which one it is. So in order for us to pinpoint and pick the pKa's that we have to average together, so the pKa is or the PI is equal to the pKa of -0.5 plus the pKa where the charge is plus 0.5 divided by 2, so it's that average. So, but the question is, if we have 4 different pKa's, it's not like glycine where we just know by default. We have to figure out which is which. In order to do that, we have to figure out the charge at each pKa. So when I tell you to calculate the PI of a peptide, you have to know that you have to look at the pKa's. Okay? All right. So I went ahead and table already of how I would recommend doing this. So again, put the pHs in the, I guess, along the y-axis or the rows, and then put the groups and their respective charges at each pH in the column format. And then I have each pH equals pKa. So let's go ahead, get started, and fill this bad boy out. So if we were to look at a pH of 2, which is the pKa for carboxylic acid, we would know that the N-terminal carboxylic acid would have a charge of -0.5. Why? Because if we have a pH of 3.2, where the pH is equal to the 2, where the pH is equal to the pKa, if we were to look at our pH scale, when the C-terminus is below a pH of 2, it's protonated and it carries a neutral charge. When it's above the pKa, it's deprotonated carrying a negative charge, so it is negatively charged. So the average, if there's a 50-50 ratio on the pKa, then we would have a charge of minus 0.5. Okay, let's look at the other groups. So for the N-terminal amine, pKa of 9.5, the pH of 2 is less than the pKa, so we would have a charge of +1. The same thing applies for lysine, that where the side chain has a pH of a pKa of 10.5, we have a +1. But then we have glutamate. And so glutamate has a pKa of 4.2. So the pH again is also less than the pKa. So we protonated, but because the glutamate side chain is a carboxylic acid, it would be neutral. So we're going to have a total charge minus 1.5 or plus 1.5. Okay, let's move on to the next. Let's move on to the next pKa. This is the pKa for glutamate of 4.2. So carboxylic acid for the C-terminus is going to kick over completely to 1 because the pH is greater than the pKa now. Similarly, we're not going to see a change with the lysine or the N-terminus. They're both going to be +1 because the pH is still less than the pKa for those two residues. And then finally, if we look at glutamate though, glutamate, it's the same thing that we saw with the C-terminus, except instead of being at 2, we're at 4.2. And so if we're half protonated, half deprotonated, that means we're half neutral and half negative. So the charge would be a net of negative 0.5. And if we add those two together, we get a charge of minus 0.5, or plus, 0.5. So next we'll move on to, and when I do these, I like to look at the groups in order of increasing pKa on the pH scale. So I start with the lowest pH pKa and move up to the highest. So you're starting with your acids and moving up to your amines, essentially. Okay, so now we look at the average pKa for the side chain or the amine. And so this one is a pKa of 9.5. And so we know, again, we're still going to have a negative charge on the both of the carboxylic acid groups for the C-terminus and the glutamic acid, because the pH is going to be greater than the pKa of both of those. When we're at pH of 9.5, we're still less than the pKa of the side chain for lysine. So that one will retain a positive charge, or charge of +1. So that leaves us with the N-terminus. And so again, if we have a pKa of 9.5, we go from 0 to 14. When we're below the pKa, we're going to be protonated or positively charged. When we're above the pKa, we'll be deprotonated and be neutral. So when we take the average of this, instead of the charge being negative 0.5 like we saw for the acidic residues, for the positive residues that are positively charged at the physiological pH, we're instead going to see a value of positive 0.5. So when we add these all together, we're going to get a value of negative 0.5. And then finally, if we look at our last pH, the carboxyl groups for the C-terminus and glutamic acid aren't going to change. And lysine the N-terminal amine will be 0 because it's going to be mostly deprotonated now. However, for lysine, it's the same thing that we saw with the N-terminus, where we're going to be half protonated with a positive charge and half deprotonated with a neutral charge, giving us a charge of positive 0.5. And so if we were to add those charges together, we get a charge of negative 1.5. And if we were to look back at this titration curve, we'd have a charge of positive 1.5 at the first pKa, positive 0.5 at pKa2, negative 0.5 at pKa3, and negative 1.5 at pKa4. Now I told you that the shortcut to figuring this out is finding where the pKa changes from +5 to -0.5 or vice versa, and then take the average. So 4.2 plus 9.5 divided by 2. And that would make sense where we're on the chart, it would be halfway between those two pKa's on the titration curve. However, this is because if you were in the region between those two regions, once you were to step away from the pKa and look at a region in the middle, say pH of 5, you're going to have a net charge of 0. And if we were to go through and do the math for that, let me pull up my calculator. You can also take this opportunity to do your calculator. We get a pH of approximately 6.9 for the PI. All right, and that about sums it up.